Hello, this is the seventh video in a little mini series I'm doing on characteristic functions, moment generating functions, factorial functions. This is part two of our moment generating function portion of this little mini series. Now, I probably should have done the properties on page 2 first, but I didn't, but we'll just jump right in. So if we have a moment generating function, or let me rephrase that, these two statements are equivalent. The moment generating function is finite in an open interval Tn to Pn. Now n means that this is a negative number and p means this is a positive number. So this is an interval that captures 0. Now this is true if and only if the tails of f are exponentially bounded. And what that means, the probability of being greater than some x is less than or equal to this exponential function, where c is positive and t0 is positive. So let's look at the proof here. So let's assume that the moment generating function is finite for some t greater than 0, and we're only going to look at the right tail. The left tail is done similarly, and due to time I'll let you do that on your own. So if we look at the probability of being greater than x, we can take each of these times t and then exponentiate both, and we get this. So these are this equal in probability, and this is Markov's inequality here. And then if you take the exponential function up, you get this. And so this looks like an exponential function if c is this moment generating function and b is t0. I guess technically that should be t0, 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 t0. So if the moment generating function is finite, then being in the upper tail is exponentially bounded. Okay, and then you can do the left tail similarly. Okay, so that's going to the right. Now going to the left, we assume that it's exponentially bounded, and then we'll show that the moment generating function is finite. So here is the just definition of moment generating function, and that means that's equivalent to this. So then the reason that this is true, that this random variable is positive, okay? So then we only need to consider the positive cases of y. And actually I have a video on this. You can search expected value in my videos. But we can break this piece in from 0 to 1 and 1 to 0 and look at it this way. This is equivalent to this. Now, the probability is less than or equal to 1. So we can just make this 1, and then we get a less than or equal to sign. And then this doesn't change. We take the log of both sides and divide over by t. So this hasn't changed, only this bound has. But here we're assuming that x is exponentially bounded in the tails. So this piece is 1, so it comes straight down, but we replace this by the exponential bound. And then we take the t, since that's log of y, we can take the t to the top of that, the minus t0 t, and then the e and the log cancel, and we get this. Okay, but when is this bounded? This is only bounded if this exponent is greater than 1. It has to be negative. So maybe it's less than -1 would be a better way to say it. Or if you just look at this piece, t0 divided by t with the negative out front, it's saying this is greater than 1. So when t is less than or equal to t naught, then this is bounded. And so we've proved it both ways. Here are some just random properties. I think they're pretty consistent, and most of these follow because the moment generating function is actually a characteristic function if you stick in I to it. So in all of this, we're going to assume that the moment generating exists in a neighborhood of 0. So for all t less than t naught. So here, yeah, the moment generating function can be thought of as a characteristic function. Number 2 is pretty powerful. There's a one-to-one correspondence between the density and the moment generating function. And we're going to use this property in our example. The moment generating function can be thought of as the moment generating function because by definition it's this, and that using a Taylor expansion is this. And then you can take the expectation through and you get this. And so like these are the moments of the density F. If we take the nth derivative, it's this. Assuming we can take it through the expectation, we get this. And the nth derivative is this of the exponential function. And so if we evaluate the nth derivative at 0, we just are left with the nth moment of x. Linear combination of x is this, and then you can take out the constant piece and you're left with this, but this is just the moment generating function of x evaluated at tb. And so we're going to make use of that in our example. And then if x and y are independent, so x plus y is this, but the t can be distributed and then the e's can be broken apart. But since they're independent, we can take them as a product. Well, that's just the moment of x and the moment of y. So now let's do an example with moment generating functions. Let's look at the central limit theorem. And so this is just the brief, look it up online for more detail, but it's essentially if the sample mean converges to the population mean with probability 1, then this sum goes to the standard normal distribution. So we centralize it, so subtract the mean, divide by the standard deviation, multiply sometimes some constant, and it's a normal distribution. Now the proof of this I saw 2-3 weeks ago on YouTube. It was a Harvard University video, and it was a lecture on the central limit theorem. And I hadn't seen this proof. Actually, I think I have the proof of the central limit theorem in one of my videos, but I haven't seen this version, and so I thought it was pretty neat and would include it in the moment generating function series. But it's I don't know how popular it is. I hadn't seen it, but I saw it in this video. So equivalently, if we can factor out an n everywhere, then this is equivalent to this. Okay, so we want to show that this goes to standard normal. Okay, and then we're going to assume that the moment generation function exists for each xi, and without loss of generality, assume it has a mean of 0 and a standard deviation of 1. So we could standardize these, subtract the mean divided by the standard deviation, and then look at the yj's, how they behave, and go to standard normal, and then you can kind of back transform it. But we'll just assume that they're 0 and 1. So let's let Sn be this partial sum, and we want to show that the moment generating function of Sn divided by square root of n. So really, if the mu is 0, that drops out, and if this is 1, it drops out. So really, that's where we get this. We want to show it goes to standard normal. So if we look at the moment generating function of Sn over square root of n, it's this by definition. And since this is the sum of independent random variables in one of the properties, property 6, we can take it as the product of the the moment of x1 x through xn, but each of these are independent and identically distributed. So really this is the same as this. So we can just look at the first one and then raise it to the nth power. But this is the moment generating function evaluated at t over square root of n. Now if we let n go to infinity, we get 1 raised to the infinity, because if we let n go to infinity, this piece goes to 0, and the moment generating function of 0 is 1. So that's where we get the 1, and this is infinity. So it's sort of an undefined limit. We can't make a conclusion. So let's take the log of both sides of this piece here. And so if we take the log of this, you know, we can bring that n out front and maybe do something with that. And that's what we're going to look at. So again, we're still taking the limit as n goes to infinity, and if we took the log of that, n comes out front, and we're going to take this down and down as red pen black pen calls it into the denominator, so this becomes a 0 over 0. So this is clearly 0, and this limit goes to 0. The moment generating function of 0 is 1, the log of 1 is 0. So we get a weird situation there. And these are integers, so let's convert it to let y equal 1 over the square root of n, and that becomes a real number. So you plug in y here and you get y squared, and this just becomes yt. And so this still becomes a 0 over 0 situation. So let's use L'Hopital's rule. Take the derivative. Well, the bottom is easy, it's just 2y. The derivative of a log of something's 1 over that, which is this, and times the derivative of this, which is this, times the chain rule, which we get the t out front. So one note before we proceed, let's look at the moments of a standard normal distribution. So here's the moment generating function, and if you evaluate it at 0, you get 1, right? The expected value, oh, that should be the expected value of e to the tx, darn it. So you evaluate it at 1, e to the tx, you get this, and the first moment is the mean of a standard normal, which is 0, and the second derivative is its expected value of x squared, but since the mean is 0, that's the variance. So this becomes 1. And I drive these moments in a video that I called the first 4 moments of a standard normal distribution. If you want to search that, you can find the derivation. So let's break this into pieces. The 2t can come out front, has nothing to do with y, and then break this into the product of two things. So if we look at this product, it as y goes to 0, this goes to 1, and it essentially goes away. So then let's just look at this piece here, and you still get a 0 over 0 situation. Because this goes to 0, and the first derivative evaluated at 0 is 1. And so, 0. And then, so let's use L'Hopital's rule again. So here, the bottom we get 1, and here when we take the derivative of that, we get the second derivative, but the chain rule says we're going to get another t out front, and we get this t squared. So now when we let y go to 0, well, that's 1, it stays 1. The second moment, or the second derivative of the moment generating function evaluated at 0 goes to 1, so this goes to 1. So this piece goes to 1. So we're left with t squared over 2. Now, so that tells us the log of the moment generating function goes to t squared over 2. So let's take e to both sides, and we get this. So the moment generating function of that sum goes to this, e to the t squared. But we haven't shown this, and the examples coming up, we're going to show that that is the moment generating function of this standard normal random variable. So that tells us that this sum goes to standard normal. because moment generating functions uniquely determine a PDF. Anyway, I hope you enjoyed it. That's all I have for this. Next video is going to be on factorial moments and potentially joint moments, so like a bivariate distribution or trivariate or etc. Please like the video if you did, and subscribe so you don't miss the next one. Thanks. Bye.